How does molecular replacement work?
Imagine you had just carried out an X-ray crystallography experiment on a protein crystal containing an unknown protein. To get from there to the protein structure, you first need to carry out an inverse Fourier transform to calculate an electron density map.
To solve the equation, you need to know three things: wavelength, amplitude, and phases. We get the wavelength from the index of planes and the amplitudes from the intensity of the experimental structure factors. But what about the phases? Unfortunately, we cannot get the phases from the experimental data. This is known as the phase problem.
There are several solutions to the phase problem, but one of the most common methods is molecular replacement, MR. From 1970 to 2013, almost 80,000 protein structures were solved using molecular replacement techniques, which is about 60% of the structures in the protein data bank. The idea behind MR is that proteins with at least 20% sequence identity will usually have similar 3D structures, and therefore the phases for the model could be a good first estimate for the unknown phases.
To try and simplify things, we're going to use hands as an analogy for proteins. Say you're trying to find the structure of a human hand. You have the data about the number of bones and fingers, but you have no idea how they're organized into the final shape. So, you would search the Animal Body Parts database for a similar structure. You find a spider monkey hand. There are some differences, like the number of digits or the shape of the palm, but they are similar enough so that the model hand can be used to build the human hand into the right shape.
Now you understand the concept behind molecular replacement, but how does it actually work? Firstly, when you find a suitable homologous model, it's not going to be magically aligned with your unknown structure. It needs to be rotated and translated into place within the unit cell. You don't have the same kind of information for the homolog and the unknown, so you need a way to compare and to superimpose them. There are several ways of doing this, the main ones being the Patterson method and the maximum likelihood method. The first method uses the Patterson function, a modification of the electron density function that doesn't require the phases. Instead of the electron density map, it creates a map of interatomic vectors. Depending on the space group of the crystal, the map contains sets of A, intramolecular vectors within the protein, and B, intermolecular vectors between asymmetric units. Having the Patterson maps for both the homolog and the unknown, the model map is rotated, and how well the new orientation matches the observed data's map is calculated mathematically. This is repeated until the best match is found. Then, the protein is translated within the unit cell, using information about the symmetry within the space group. Again, maths is used to find the best match for the observed data via correlation search.
The other method, currently used by automated programs like Phaser, is the maximum likelihood method and is based on probability. In Phaser, the atomic coordinates of the potential models are converted into structure factors, and the root mean square difference, RMSD, of the alpha carbon atoms between the experimental data and the model is measured. Maximum likelihood-based rotation and translation functions are then applied for all models, and the program identifies the most likely model in the specific orientation and position that would result in the experimental data. When the rotations and translations are defined, a Fourier transform can be performed on the atomic coordinates of the model, and the resulting phases can be transferred to the correct set of planes. The phases can then be used alongside the experimental data. Congratulations, you can now start building and refining your structure.
Now let's have a look at a real example. In 1999, researchers solved the structure of human C-reactive protein, a blood serum protein involved in responses to injury and infection, which complexes to phosphocholine. The structure of CRP was determined using another protein from the same family, serum amyloid P, SAP, as a search model. as they have 52% sequence identity. Both proteins bind calcium, but SAP complexes with acetic acid rather than phosphocholine. Like SAP, CRP was found to be a pentamer with 10 calcium binding sites, but also has 5 phosphocholine binding sites. To find this out, X-ray crystallography was carried out on CRP, and molecular replacement was used to obtain a model.
Here are our references if you want to find out more.